We've talked about how electrostatic potential is analogous to elevation, and so just as masses will go from a higher elevation to a lower elevation, falling or rolling downhill, we know that positive charges will move naturally from a higher potential to a lower potential. And we know that negative charges do the opposite of what positive charges do, so negative charges will move naturally from an area of low potential to an area of high potential. So if you have a voltage between 2 points, then we know that charges will want to move between those 2 points. Which direction they go just depends on which sign of charge they are. The amount of current that we would measure flowing through a conductive material is proportional to the voltage applied to that material. The more voltage, the more current. However, even conductive materials resist the flow of current to varying degrees depending on the material that they are made of and the temperature and the shape of the material. The table on this slide has to do with how much the material itself matters. That table was a measure of something called resistivity of a given material. So how much resistance there is to electric current flow through a material has to do with the following variables. The resistance R is equal to the resistivity, and that is a Greek letter rho. That's not the letter P. It's the same Greek letter rho we use in Physics 140 to talk about density. So again, we're recycling our variables, and I apologize for that. But this is called resistivity, and it's a different value for every different material. That's what that table on the previous slide was. You would be able to look up the resistivity of a given material if you weren't given it in a specific question. So I'm sorry, the resistance of an actual object is equal to the resistivity of the material it's made out of times the length of the object divided by the cross-sectional area of the object. Once we've established the resistance value for an object, we can talk about the amount of current that would flow through the object when the object is subjected to a voltage. Usually when we talk about this, we are specifically talking about the positive terminal of a battery being connected to one side of the object and the negative terminal of a battery being connected to the opposite side of the object. This is the symbol we use in circuit analysis to describe a battery. And this is the symbol we use in circuit analysis to describe an object with some electrical resistance. And these connecting lines are used to describe wires. Now, wires do have some resistance to the flow of current, but for most applications of studying circuits, we assume that wires do not have any resistance. So as you learn to analyze circuit diagrams, you will treat connecting lines as perfect conductors. So for example, in this image, if this wire is a perfect conductor, then it has no resistance to current flow. The entire length of the wire is equipotential at the top of the picture. There is no delta V between the positive terminal of the battery and the place where it is connected to the resistor. The same is true along the wire at the bottom. That means that the amount of voltage that is provided by the battery must be entirely dropped, is the term we use, by the resistive element. That is where the voltage changes from high to low. The equation that appeared briefly on a few of the earlier slides is called Ohm's Law. It's that the current is equal to the voltage over the resistance in any material. I have this image of Georg Ohm up mostly so that you know that Ohm is someone's name. So Ohm's law is much like Newton's laws or Hooke's law or Coulomb's law. It's named after a person. And I wanted to tell you that because we use an omega as the unit for Ohm's law because omega and ohm sound so much alike. So I wanted you to know that was actually someone's name though. Georg Ohm published Ohm's law sometime in the 1820s. And again, it relates the amount of current flowing through a material to the voltage that is provided to 2 different points in the material and the resistance in the material. So for example, the way it would be used is something like this. If a 1.5 volt dry cell is attached to a resistor, the resistor is rated at 4.00 kilo ohms, and we assume that the wire itself has no resistance. What is the amount of current that would flow through this circuit? And what we would say is the amount of current is equal to the voltage applied divided by the total resistance. If the voltage applied is 1.5 volts and the total resistance is 4 kilo ohms, then we can calculate that the current will be 375 microamps. So Cool, that's how Ohm's law works. But what is the point of resistance? Do we want it? Is it a good thing or a bad thing? Check out the next video to find out.